And I'll share my screen. And we'll get back into it. We're 8 pages in of 14 pages, so we have 6 to go. I think we'll do good. We just talked about general Hooke's law, and did the two of you, did you look at this closely when you took ME 216? Was that covered fairly thoroughly?
Yeah, Dr. Romkey's last semester beat it into us pretty good.
Good deal. I'm glad.
I know I had to memorize all of those for the final, since it doesn't do note sheets.
Yep. So this is a good thing. And you have similar relationships for shearing strains, where your gamma YZ is just 1 over your shear modulus G times tau YZ, but it doesn't get complicated like the normal relationship for that, the normal strains as we saw above. So they're just directly tied to one another. And so in this process, we've really defined 3 material properties: the Young's modulus of the material, the shear modulus of the material, and the Poisson's ratio. But there's only 2 of those that are actually independent. If you know 2 of them, you can solve the third. And so G, the shear modulus, is approximately equal to the Young's modulus divided by the quantity 2 times 1 plus nu. And this is really only true if the material is perfectly isotropic. As materials deviate away from this, if you were to measure these 3, you'd see that deviate away from that equality sign. But that'll give you a good ballpark estimate for most of your general isotropic materials. And then when you're dealing with plates and shells, you often end up with plane stress or plane strain conditions. And that's just where certain stress states are equal to 0. And so it does simplify down your 3 equations and oftentimes 3 unknowns in that process. And so for plane stress, that's usually plates and shells, thin materials that are axial loaded in the plane of the materials in either direction, so that there is not a stress through the thickness. Likewise, there's no shearing stresses through the thickness on the ZY plane or the ZX plane. And so that's typical for thin bodies. And then plane strain is typical for larger bodies that are constrained from displacing. Think, for example, of a dam wedged between 2 mountains. It's not going to contract or expand in that process. And so a strain in the Z direction would be 0, and similarly with the shearing strains involving that Z direction. One thing that we'll notice though in that, if our strain Z is 0 up here, that doesn't mean that our stress is 0 in that Z direction. And so we'll take a look at that quick. Strain Z 0, we can multiply both sides by E. E times 0 is going to be 0, so left-hand side is still 0. E cancel on this side. And so we find that sigma Z is just equal to nu times sigma X plus sigma Y. So plane strain does not necessarily mean plane stress, so that there would be a stress that develops there. And a lot of this really oftentimes depends on the boundary conditions for the given problem in determining what the 0 values are for the state of strain or the state of stress for the given problem. The plane stress condition, if we touch back on that one up here, where sigma Z is equal to 0, we can relate that down to then similarly that strain in the Z would not be equal to 0. If we have a plate that's being stretched in both directions, it's going to typically thin the plate out. It's going to contract just like we see with axial loading. It contracts in the transverse direction. And so if we're dealing with plane stress, sigma Z is equal to 0. So we don't have to worry about that in equation 1 or equation 2 in terms of multiplied by nu. And then strain in the Z, sigma Z would be equal to 0. So we just have that minus nu over E term times sigma X plus sigma Y. And so again, we note that plane stress does not generally mean a case of plane strain. And so with this plane stress condition, it can be beneficial to solve for then the stress for each as a function of strain. And so that's just a bit of a derivation to go through that to rearrange these to solve for sigma X and sigma Y. And I guess I'll step you through this. For the second one, solve for sigma Y. And so it'd be epsilon Y, strain of the Y times the Young's modulus is equal to sigma Y minus nu sigma X. And so sigma Y would be equal to epsilon Y times the Young's modulus plus nu times sigma X. That we could substitute in for equation 1, our sigma Y term. So strain in the X is equal to 1 over E times sigma X minus nu. And sigma Y we just solved, strain in the Y times epsilon plus nu sigma X. And as we go through that, we can then simplify. Let's see. This I multiplied both sides by E to get that over on that side. And now solving for sigma X, we'd have strain in X times Young's modulus plus nu times strain in the Y times Young's modulus plus nu sigma X. So you can see we're working on solving for sigma X here. And next thing we can do is get all the sigma X terms over onto the left-hand side. So we'll subtract this off both sides. So sigma X minus nu squared, sigma X is equal to E over E times strain in the X plus nu strain in the Y. And what we did there was we just pulled E out of those first two terms. And then we can pull a 1 minus nu squared out of here, being multiplied by sigma X, and then divide through by that 1 minus nu squared term. So we end up with sigma X is equal to the Young's modulus over 1 minus nu squared times the quantity strain in the X plus nu strain in the Y. And so with that, for the plane stress condition, we can solve then what sigma X is based on the Young's modulus, Poisson's ratio, and the strain in the X and strain in the Y measurements. They probably discussed that too in ME 216. Typically what you're doing is measuring, say, surface strains, for example, with rosettes. And so these values, strain in the X and strain in the Y, would be values that you would be measuring for a plane stress condition that's being applied. And then with that, you can solve then the corresponding sigma X value. The same would be true for sigma Y. We would just swap the variables. So sigma Y would be equal to E over 1 minus nu squared times strain in the Y plus nu strain in the X. And so that would transfer accordingly. Let's see, we already talked about that relationship between shear modulus, Young's modulus, and Poisson's ratio. Only need to measure 2 of the 3. If you measure all 3, you'll find that it's an approximate relationship. and valid for linear elastic region for isotropic materials. And so here's another example where we can actually put numbers into it. This is where we have 10 millimeter wide, 10 millimeter deep into the page, and 25.4 millimeter block of rubber type material that is going to be pushed into that 25 millimeter hole. The Young's modulus of the material is 1.4 gigapascals, and the Poisson's ratio is 0.4. And so what we want to find then is that load P that's required to push the block into the hole until the surface is flush. And so this is just a nice problem to make use of the 3D Hooke's law to really figure out what that load P is. If all it were an axial loading condition and it were free to, in this case, if it were free to expand in the transverse direction, we could just use the delta equals to PL over EA to solve for that displacement of 0.4 millimeters that would be needed to compress at that distance. But we are constrained here within this block. So it's going to take a greater force to push that rubber-like material in there because they'll be fighting Poisson's effect in that process. And so for the analysis then on this, we need to take into account that full 3D state of stress and the conditions on the strains and things like that in the process. So for this problem, I have X set up to the right, Y vertically upward, and so Z is then out of the page. And so in this scenario, the strain in the X is going to be 0 since it's not allowed to expand outward. It's constrained in this location. And same thing with the Z direction out of the page if it's also 10 millimeters wide in this hole. And then we then have both of those strains equal to 0. The strain in the Y direction is still going to be that same relationship for, say, the final length minus the original length over the original length. So 25 minus 25.4 over 25.4 will give us a strain of minus 0.01575 meter per meter. So that is going to be our actual strain that we're looking at. And so from Hooke's law, we then have all the terms on the left-hand side. For our general Hooke's law. And so we have all three of our terms on the left-hand side, and we then have our unknowns of the stress in the Y, X, and Z directions, or X, Y, and Z directions. And so we have a system of 3 equations, 3 unknowns, really to solve for those 3 stress values. So there we go, Hooke's law. We know strain in the X is 0, strain in the Z is 0, strain in the Y, the minus 0.01575. When these things are equal to 0 here, we can cross out the E's, multiply both sides. And so we have our 3 equations there. And in this case, you would note that sigma X is going to be equal to sigma Z, since strain in the X is equal to strain in the Z, and the geometry is the same as well. If you would have a gap in one direction, say for example, there was a gap in the Z direction, that would allow that material to expand up to where that gap would be. And so it would allow the material to strain up to that point. And there would be then a positive strain. If that were the case, then you would have to solve all three equations, three unknowns simultaneously. With seeing the symmetry in this, we know that sigma x is going to be equal to sigma z. And so process on solving equation 1 up there, solve sigma x from equation 1. And so we'd have sigma x is equal to nu times sigma 1 plus sigma z, which we're defining as sigma x, stating that that's equal to one another. And then if we were to move those variables to the left-hand side, we'd have sigma x minus nu. Sigma x is equal to a nu sigma y. And if we pull a 1 minus nu out of that, we'd have sigma x is equal to nu sigma y over a 1 minus nu. So this would be our relationship between sigma y and sigma x. You can state the same thing. Sigma z is going to be equal to nu sigma y over 1 minus nu. With that, now we can put equation 4 into equation 2 for each of those terms, sigma x and sigma z. And so we have the strain in the y direction, sigma y minus nu sigma x plus sigma z, which again is sigma x. And so that would be a minus nu times, now making that substitution and multiplying it by 2. Since we have two terms, we'd have 2 nu sigma y over 1 minus nu. Solving, what we're solving for is sigma y. We want to know what the stress in the y direction is. Primarily from all this, and we're getting things all in terms of sigma y at this point. And so with that, we can pull sigma y out of there, and we'd have a 1 minus 2 nu squared over 1 minus nu. And then sigma y is equal to just dividing that through for that term. And I think, yeah, we had the material properties that were given. And so we can calculate that out. I did this in terms of megapascals, so 1.4 times 10 to the third megapascals, 0.4 for the Young's modulus, or for the Poisson's ratio. And so everything just kind of collects in there, and you find that sigma y is equal to a minus 47.24 megapascals. So it is in compression. And so we really needed to make use of the full 3D Hooke's law in order to calculate then what the stress was in the y direction. We really would not be able to do that with the 1D loading condition methodology, because we had to take into account Poisson's effect. And we know that this stress sigma y is just going to be that force applied over the cross-sectional area. And that cross-sectional area is 10 millimeters by 10 millimeters. And with that, we would then have our stress that we calculated, and we'd then multiply that by 100, essentially. 10 by 10 is going to be 100 millimeters squared. And so 47.24 megapascals times 100 millimeters squared will give us a load P of 4,720 newtons. And so that is the answer to the question of what is the load that is required to push that down to make that flush. But then a follow-on question for that could be, what then is the stress in the x or the z direction? And so if we kind of scroll back up here, we know now what sigma y is, minus 47.24 megapascals. So all we would have to do is plug that into equation 4 with our Poisson's ratio 0.4 times sigma y over 1 minus 0.4. And that would give us our stress in the x direction. Remember, this is a negative value compression, and what the material would really want to do if it was unconstrained is just expand outward in the transverse direction. And so since it's not being allowed to expand, is being constrained, so sigma x will also be a negative stress, stating that it's in compression as well. And that'll work out. This nu is positive 0.4, 1 minus 0.4 is 0.6. So sigma x will come out as a negative value as well. Let's see, are there any questions on that example problem? We're getting closer to finishing up here. The next topic is looking at thermal strains, where alpha is your coefficient of thermal expansion for the material. If you look in the back cover of your Hibbler textbook, it has both tables set up in the English engineering system and the SI unit system of material properties for common materials, and the coefficient of thermal expansion is included within that. But that's really referring to the strain that's caused by 1 degree change in temperature if it's unrestrained. So thermal strains occur due to that change in temperature. And so if you have, say, a steel bar that you set outside, it's going to heat up. If it's unrestrained, it's just going to naturally expand due to that increase in temperature. And so it'll end up with a longer bar. It's going to be slightly bigger in diameter because it wants to expand in all directions. The only time you end up with thermal stresses is when that object is constrained. And so I think we'll get down to that in a second here. But that thermal expansion, that thermal strain, is just going to be equal to the coefficient of thermal expansion times the delta T that it's subjected to. And also superposition applies, so that the total strain is just going to be the sum of any strain due to stress that's being applied, plus any strains due to the thermal effects. And so you can calculate the total strain. And then again, the thermal stresses only occur if that object is constrained from expanding or contracting. If it's not allowed to do what it wants to do, it's going to build up stress in that process. And so a good example of this is the HVAC system for the Rapid City Regional Hospital. They have their powerhouse a good distance, I'd say about a quarter of a mile from the hospital itself. And what that does is just provide backup energy in the case of power going out to the rest of the area from Black Hills Energy or wherever it's coming from. So if power goes out, they have their backup power capabilities there at the regional hospital. But then they run all sorts of coolant and things like that between the powerhouse and the hospital as well. And so they have all these pipes running to and from the hospital. And it's underground. There's long stretches of pipe, and to prevent thermal stresses from developing in those long stretches of pipe, they have flexible couplings for each one of those sections. And so it really provides that ability for the pipe to expand and contract as needed and not develop stress. You'll notice the same thing with bridges and things like that too, where there's generally going to be a gap in those to allow for the expansion and contraction of that bridge. So that's one way thermal stresses can develop. Another way that thermal stresses can develop is if you have a thermal gradient. So there's a varying temperature through the thickness of the material. That would make sense when you start looking at heat transfer, Me313, and looking at conduction, the heat transfer through a body, and realizing that there's going to be a temperature gradient through that object. With that being the case, the material wants to expand or contract at different rates through the thickness, and so that can cause thermal stresses to develop. And then likewise, if you have different materials bonded together that have different coefficient of thermal expansions, they are then in a epic battle with one another. One wants to expand more than the other, and they end up warping and deforming and building up thermal stresses in that process. And so those are all things that really need to be considered when you are dealing with situations of large temperature changes and what effect that will have on any thermal stresses that build up. The nice thing about Hooke's law and thermal strains is all we have to do is add an alpha delta T to all three of those expressions. And we can then take into account those thermal effects as well. And so it doesn't really change things significantly to take into account thermal effects. And you could go through examples just like the one we just went over. And if we added delta T to that, we could take that into account as well in solving our sigma Y value. For that case, if the delta T were positive, the material would want to expand, but it wouldn't be allowed to. So you would have to have a higher P pushing that material down into the hole. If the delta T were negative, it would cause it to want to shrink, which would really help you out. It would reduce the amount of force that would be required to push that into the hole to make that flush. And so this is just getting into a little bit more of the uniaxial thermal effects, just taking that into account from Hooke's law. And so if we have an alpha delta T that is unconstrained, we could find the corresponding displacement in the x direction. And so strain in the x is 1/e times sigma x minus nu sigma y plus sigma z. And again, if it's unconstrained, it's not going to develop any stresses at all. So these are all going to be 0. And we'll just have an alpha delta T as our strain. And strain again is just sigma x over L. So our displacement then and the x direction would be alpha delta T times L. And so that's how much it would want to expand. On the opposite end, if it is constrained, then that's going to force your strain in the x to be equal to 0 instead and result in stress in the x direction. And so from Hooke's law, sigma epsilon x would be 0, sigma y, sigma z would be 0, and we can solve for sigma x. If we multiply through both sides by E, we would also have to multiply alpha delta T by E as well. And moving that to the other side, sigma x would be equal to minus E alpha delta T. And so again, if you have an increase of temperature, it would want to increase its length. But since it's constrained, essentially think of it being pushed back to what the constraint length is. And so that's placing that into compression. And I think that's oftentimes how we'll look at statically indeterminate systems, is we'll take a peek at what happens, what if there wasn't a constraint there, where would it deflect to, and then what force would be needed to push that back to the constrained position. And so what we see is, again, that alpha, and that's positive. If you have then a positive delta T, so temperature increases, that's going to result in a negative compressive stress in the X direction. And then if alpha positive, if we have a decrease in temperature, that would cause the material to shrink. And so if it was just fitting in there, just enough for friction to hold it, for example, when it shrink, it would just fall if it was unbonded or not secured to that position. And so that is kind of a nice background then on chapter 1, 2, and 3, dealing with stress, strain, and material properties. And then chapter 4 is going to deal more with axial loading conditions. And so taking into account these thermal effects, taking into account the statically indeterminate loading type conditions where you need to solve for those. And so this is really a good stopping point for today. And then we'll be able to pick up on chapter 4 then on Friday this week. And so I'll stop sharing my screen again. Let's see, are there any other questions that you have over this stuff? And then the advice I have really with the homework is it is going to take a bit of time to get through that. And so with the homework being due on Saturday, we're kind of covering that material right now this week. And so my recommendation would be to try to do as much homework as you can over this current weekend, so that if you have any further questions, you can bring those up next week during class. And then that way you're all squared away for next week. You're mostly done with the homework. If you have a few questions, you can bring those up, but then you're all set to submit those towards the end of next week into Saturday timeframe. And then that'll set you up well, because then next week we'll be covering torsion, and I'll get the assignment posted. So then you can focus more than next weekend on your torsion problems, so that you're kind of doing the homework as we're learning the material, as opposed to waiting until the last minute, the last couple days before it's due. That's going to help you, because if you get behind, that's a lot of homework to catch up on. So I guess my main recommendation is to make use of this week and this current weekend to work on that homework that's due for next Saturday. Let's see, are there any other questions?
No, I don't have anything.
All right. Well, thanks for joining in, both of you, and we'll see you on Friday. Thanks for your time.
Thank you.
Thanks. See you on Friday.
Yep. Bye.